So today we are pleased to welcome Dr. Fanny Baumann. Fanny completed her PhD in material science at the NMP Barcelona in October, where her research focused on stability testing of perovskite solar cells. Her work centers on in-situ characterization methods and understanding how perovskite solar cells respond to stress during long-term stability measurements, a very important topic in this field. She entered the perovskite field during her master's thesis at EPFL and carried out her doctoral research in the NMP group led by Professor Monica Lira-Cantu and Dr. Sonia Ruiz-Raga. Fanny, we are looking forward to your talk. The floor is yours.
Hi, everyone. Thank you, Matthias, for having me, and thank you, everyone, for tuning in. Today, we're going to be talking about multimodal tracking of strain, optoelectronics, and performance of perovskite solar cells at operation at 85 degrees Celsius. This presentation is going to be based on recently published work from us here at ICN2 in Barcelona, and we will also see some other features from other works that I've published during my PhD thesis. So let's get started. We're going to go through the methods, and we're also going to go through some of the results. We have quite a few slides to go through, so bear with me and hope you don't hesitate to reach out if you have any questions. I will assume that you're all aware of halide perovskites and some of their potential applications, such as solar cells. When we want to use halide perovskites in a solar cell, we utilize that they have a direct, rather adequate band gap with large charge separation and long carrier lifetimes. And thanks to this, we can just sandwich the perovskite layer between adequate selective layers to extract electrons and holes at either side of the device. And when the device is illuminated, we can obtain an internal electric field and electricity. We see that it's important to generate sufficient electronic carriers inside the device and also have a large internal electric field and also extract devices charges efficiently so that we can get the highest possible power output. So record devices are reaching power conversion efficiencies above 26%. Here we are optimizing very much for stability, so we are more focused on the longevity of the solar cell than on reaching record efficiencies. It is indeed important to focus on stability, as perovskite solar cells are presenting several types of instabilities, some extrinsic and more intrinsic degradations, and it's been treated to a smaller and lesser extent, so larger and smaller extent. So we are going to focus quite a bit on intrinsic instabilities today. And some other things to take into account during stability testing is the adherence to the ISO's protocols so that we can ensure the quality of the reports, and we can also compare results between laboratories. We are going to use an light source that is closely approximated to the AM1.5G, though it's white LED illumination, and we're going to use 85 degrees Celsius during these experiments. We are also going to be mindful of strain throughout the devices and the evolution of strain over time during operation. Finally, we are going to think about the combination of different stressors applied to our solar cell. So in this case, we have illumination and heat. So we're going to be adding a lot of additional energy into our perovskite solar cell system. It's also important to consider reversibility of certain degradation mechanisms and the importance of testing full perovskite solar cell devices and not only a single layer or a half stack. With that said, we have a challenge presented to us, and that is to relate the perovskite intrinsic properties to what we can see in the full device. And there are several types of methods which we can use for in-operando characterization, but we have chosen photoluminescence, X-ray diffraction, and impedance spectroscopy. Photoluminescence allows us to study the interaction with the material and with light, both more specifically the photoluminescence of the film inside the device. X-ray diffraction lets us see the structural evolution inside the perovskites, and impedance spectroscopy lets us see resistive and capacitive changes in devices. So if we imagine the stability experiment something like this, we produce our solar cell, the perovskite is in a steady state, and we would like it to stay there. Eventually something is going to happen, and we're going to go beyond this point of no return and reach towards a more degraded state. So what we're trying to do is we're going to try to provoke these changes by using rather harsh conditions, and we are going to do two parallel experiments with in-operando characterization. So one is an operational stability test using ISOs L2 conditions with white LED illumination, 85 degrees, and under maximum power point tracking in lithos light. And the second experiment is going to be with in-operando X-ray diffraction using light and 85 degrees, again in very similar conditions, but holding the cell at an approximate MPP point after taking several JVs during the experiments. We're also going to keep the cells under nitrogen gas flow, which is room temperature, to try to reduce the influence of other stressors. Additionally, we're going to do before and after characterization. So we are doing a suite of characterization, including JV curves, impedance spectroscopy, photoluminescence, and time result photoluminescence. And we're also going to simulate some of impedance spectra to see if our observations are in agreement with what we believe are happening. And you can see we have two goals. The first goal is to perform a more extensive characterization under operation. And the second goal is to place a barrier inside the system. So this can be a chemical or physical barrier that would prevent the changes that are non-desired. So we would keep our solar cell in a more steady state, and we would have a more stable device. The barrier that we're going to use in these experiments is a combination of first additive engineering inside the perovskite layer. This is for this we're using 3-phosphopropionic acid that's added into the precursor solution, and this is from a previous work where we see that this modification with H3PP sits at grain boundaries and affects the preferential orientation, as well as induces a small compression in our devices. So we believe that it's part of the crystallization process, but it's not actively inside the structure of the perovskite. And the second part is to add a maxim flake layer here, which are the laminated titanium carbide maxines functionalized with H3PP. Then we seem to even further improve stability under illumination conditions. So this modification was not studied at higher temperatures, so we wanted to perform an extensive study at 85 degrees to see what difference we have with the stability enhancing modifications and compared to the reference cell. Okay, so this is our modification. And just to summarize the methods, we are going to use then lithos light operational stability test together with PIOS impedance spectroscopy measurements and JV. We're also going to do photoluminescence and time result photoluminescence and some simulation Setfos. Then we have our in-situ in-operando X-ray diffraction setup with similar conditions. Some automated analysis, and also I want to say that we did also impedance spectroscopy and photoluminescence analysis before and after these XRD tests, but to a lesser extent, and these were made to ensure that we have a very similar situation both before and after the test. So again, I want to just remind you that we're using temperature and light, so we're adding a lot of excess energy. And now we're going to start looking at the results. So For the little slide operational testing, we see that the initial parallel JV scans show a very similar efficiency in both type of devices. Here you can see the modification in red and the reference in blue. And at 85 degrees, you see that both devices have an initial burn-in, but the profile of the modified devices is much flatter. And this is more apparent in the after JV scans, where we can really see how the modified devices clearly outperform the reference devices. So this confirms what we believe, that the stability enhancement has an effect. And this becomes even clearer if we use our automated analysis that we built together with Sire AI user interface systems. We have very clear data for all of the cells that we have tested. In this case, it's 7 devices of each type. And we can really see that there's a characteristic decay. So it's a clear difference between the reference and the modification, with clearly the modification having another pathway towards the more degraded state, even though there's still some performance loss. Now we're going to look at this with the before and after characterization. So first we have impedance spectroscopy, which is done at varying light intensity. And this Nyquist and Bode plots are later fitted to this nested circuit, and we get something like this. So the parameter compared to the open circuit voltage that is generated in each case. So during impedance measurement, we hold the cell surrounding the open circuit voltage here. And then we can see different tendencies over time and depending on the degradation. In this study at 65 degrees, when we just look at the reference device and we see what tendencies we see over time, it can be found here. In our case, we're going to see 3 major changes, and we are going to see how they are slightly different from the reference and the modification. So in the first case, we have voltage losses, especially at lower light intensities. Second, we have a lower shunt resistance that is showing up here, and this is also a voltage-dependent shunt resistance that we're calling a Perovskite shunt resistance. You can read more about this in this paper. We're also seeing a small change in the recombination of devices, and even a little bit of a reverse relationship here. And finally, we're seeing an increase in ion conductivity, which we can see from the changes in the low frequency tau. So we are clearly having a reversibility here as well, because what you can see is that devices measured 10 minutes after the operational stability test in little slide, they are having a much larger change than devices measured 90 minutes after. I'm going to show you another example of that further on. So this reversible component seems also really more prominent at the lower light intensities. And what we did is we compared the shape of the impedance spectra, and we could see this changes with, and we could reproduce them using a Setfos. And what we saw was that we could reproduce changes much better by using changes in ion mobility compared to ion density. So what we did was we got a lot of help from Professor Juan Anta that we had recently published a paper with adequate parameters that we could copy in order to get more reliable simulations quite quickly. And what we did was we adapted it to the architecture and the values we had from our solar cell, and we added some changes in ion mobility at a constant density versus change in the density at constant mobility. So we could clearly see that for the shape that we had, thanks to having every single data from our experiments automatically plotted, we could clearly see that the tendency was more reproduced by using changes in ion mobility. Finally, with the photoluminescence, we can see that there's a loss in intensity, a slight blue shift, and we could also see that, especially in the reference cell, there is a loss of photoactive material. So at the longer time scales, there is not as much photoluminescence as in the modification, where we don't see much changes. So this really tells us something about a loss of photoemitting material. Moving on to the in-situ X-ray diffraction, here you can see the modification and the reference, again in red and blue. We have quite a lot of data coming in at the same time. So we have the applied and measured temperature. We have the unit cell length from Nelson-Riley regression, so including all Perovskite peaks with their assignation. We make a rather good estimate of the unit cell length, so the A value. And we also have the average amplitude taken from all the halide perovskite peaks and the approximated power conversion efficiency. So the power out versus the power in, taken from JV curves and compared to the light intensity, which is one sun approximated to have a similar JV curve as under an AM 1.5G solar simulator. So we're going to go through this step by step. First, at room temperature, we see again in coherently as the previous results that we have a small compression in the modification, but the JV performance is pretty similar. And as we go to 85 degrees, we start to see major changes. We have an initial very sharp voltage drop, and that recovers after a while in the reference cell. But in the start, this sharp voltage drop really shows up in the performance here at point B. And we believe that this is because in the MAXine, we have an additional MAXine layer in the modification that will really be able to compensate for some of the strain as this lattice parameter increase is very sharp. And in the reference, we have that only on one side. So in this case, we believe that it's more the fact that this is a very large strain at the interface in the reference that would not be as present in the modification. Okay, moving along, we see that during the time, there's a large development of inverse hysteresis and also a voltage drop in the reference cell, while in the modification, well, there's still inverse hysteresis, likely because of an increase in ionic conductivity, but we do not see any evolution of this inverse hysteresis. And I will bring your attention to that more, but the only thing, as you can see, is that there's a small decrease in the intensity of the halide perovskite peaks in the reference, and also there's a continuous decrease in the efficiency of the device. Furthermore, we cooled the device, and we also did some testing to see what temperatures our holder reach when we do light on and off, and we also tried to see if the heating the device to a similar temperature would produce a similar change, which we saw that it did not. So we can really also conclude here that the inner temperature of the perovskite layer is likely quite higher than the temperature that we're having if we're only heating at lower temperatures. 85 degrees, well, this was pretty stable. Okay, so just to summarize, one of the most interesting things is that we didn't see any change in the lattice parameter over time at 85 degrees Celsius. So there does not seem to be any evolution of over time of the lattice parameter. However, we see this decrease in the reference cell that really goes well together with the decrease in efficiency of the cell. So here you can see all the IVs together, and in the end, the IV curve of the recovered modification and the reference coincide quite well with what we saw in the little slide operational testing. So it was really good that we could do these two parallel tests and really compare one to the other. That provided a lot of value for us to verify what and make sense of what we're seeing here. However, we did see that there was a loss of perovskite material, and we asked ourselves, well, where is this loss going? Because if you look back here, you can see that there's even also a recovery at the end, together with the recovery of the performance. So the material should still be inside the device. So we wanted to see what happens here. So in order to do that, I just quickly have to go through this. Okay, in order to do that, we did the postmortem TEM. So we split a device down the middle and treated half of it. And in this same device, we looked at the samples treated at the identical conditions as the testing for 20 hours. And we could see that for the non-treated sample, we could clearly distinguish grains, but for the treated sample in the reference case, we really saw that there's this amorphous substance around areas with perovskite. And in the modification case, we saw that there's again clearly distinguishable grain both in the before and the treated samples. So we can see that there's just a little bit of also some new material created, but it seems to have a quite different morphology than the material created in the reference. So this is a clear indication that the formation of this layer is different in the reference device compared to the modified devices with MaxScenes and H2PP. If we look further into the composition of this new material by EDX, we can see that it has a very high carbon content. In the case of the modification, we can see it was a mixture of several elements, including TiO2. So to summarize this a bit and compare it with the impedance, we can see that, well, if we have this amorphous phase forming and it has a high carbon content, it could be a very good explanation that this is responsible for the lowering of the shunt resistance. And it also seems clear that we have a general increase in the ion conductivity over time, but there's also a very large component that could be explained by a high ion conductivity in this new material. So what we suggest is that, well, in the reference we have this core shell structure where grains are getting sort of dissolved into this new phase, and that this new phase has a lower resistance, provoking the changes that we see on impedance spectra. And in the case of the modification, well, H3PP is known to have a very strong interactions with iodine vacancies and the other prominent defects at the surface of the grains. So this could prevent the changes that we're seeing. Maybe it could hinder the ion migration, because we see even here that at the beginning, well, there's a slightly slightly higher tau for the modification as well. So we believe that this is highly related to the conduction of ions, given that the material, the new material that we see is very carbon rich, and a good carbon source inside the perovskite would be the organic cation. So final remark about the reversibility is that, while we see even on dark IV curves that we could directly relate the changes in tau to the changes in dark JVs. So it was really valuable for us to be able to do different types of JVs in a direct relation to the impedance spectroscopy measurements. So finally, just to summarize again, the loss of perovskite material of the crystal perovskite was responsible for the loss in performance in the perovskite source cells without any stability modification. But with the addition of 3-phosphopropionic acid that resides in the grain boundaries of the perovskite layer, and also this delaminated MaxScene flakes with H2PP functionalization that provides as a relaxation barrier between the perovskites and the spiral HTM, we could really see an improvement in the stability at the 85 degrees Celsius and 1 sun illumination. So we could also see how the before and after analysis together with in-situ XRD really made it possible for us to better connect the chain of events that lead to degradation, and that could lead to an improved stability, even though our modification is not perfect and still would need improvements, we really show a new way of performing stability testing. And I hope that it can inspire people to be to take in more characterization methods, such as impedance spectroscopy, photoluminescence, in operando XRD, and also to be able to do very good operational testing with many cells in parallel, so that we do not only have a single result from an experiment, but we can do some statistics. So with that said, I want to thank everyone who has been part of this work, my supervisors, Sonia Ruiz-Raga and Monica Liracanto, Masoud Karimipur, who has produced the solar cells made during this experiment, tested in these experiments. Also the fantastic technical team at ICN2, Jose Santizo has helped with X-ray diffraction analysis, Jose Manuel Casido Roque, who has helped to build this wonderful X-ray diffraction holder, Jessica Padilla, who has operated XRD with me, Bella Maestros, who has helped with the TM investigations, Marcos and Naji, who has helped with SEM, Brian for lending us the wonderful software, and of course everyone in the group. Thank you also to Fluxim for inviting me to do this talk and to spread the word about these experiments. I hope I will get many questions from you in the audience, and thank you very much for listening.
Thank you very much, Fanny, for this very interesting talk. I truly believe that, like, going towards commercialization in perovskite, it is important to have such studies which look into more details of degradation mechanisms. Thank you for your contribution. So, as I mentioned, we will do questions in the end. So please, you can now think about your questions during my part and write them into the chat. And then in the end, we will go through those questions. I just quickly say hello here again before I disappear and share my slides on Setfos 6.0, which I will use as a platform to introduce some concepts of thermal and degradation models, specifically in OLED research, to complement with Fanny's talk. So going from Setfos 5.5 to 6.0 means that there are quite a few features new in Setfos 6.0. For those of you who haven't seen yet the new Setfos, that's how Setfos 5.5 looked. And besides many new features, the developers did also a very good job in changing the user interface. So you can see here now the same file opened up in the new Setfos 6.0. So the appearance is, I would say, a quite professional look. So let me now introduce you some of the new models which are in Setfos 6.0. I will not go through all of them, but I want to mention one other model which is inside because it also relates to degradation of perovskite, which is the tunneling model, and one important factor in degradation of perovskite is also reverse bias, specifically when going towards thinking about module application, where you have shading of a cell, which leads to reverse bias of solar cells. So to understand this breakdown, as you can see here on the bottom left of a solar cell, we looked into this in a project with a recent publication of a colleague of mine. You need to understand the tunneling, or you need to have a tunneling model inside to get this breakdown, which is partly due to strong fields you have then at the interface, which means they are also influenced, as you can see here in this graph, by ion density, which modifies the electric field. So first I will introduce the degradation model, and it's even labeled here OLED degradation model, since big part of introducing this model is coming from the OLED field. You can also apply it to solar cell to perovskite, but I will show now the OLED side. Well, first, for those of you who are not familiar with OLEDs, from a solar cell perspective, with respect to recombination, what you care about is just decreasing recombination as much as possible, get rid of dark chocolate tall recombination. You can't get rid of the radiative recombination, but essentially in the solar cell, at first approximation, you don't care about it. But in OLED, the story continues because what you care about is an exciton that forms if you have radiative recombination. And this exciton, this is a charge pair which is not separated. In the end, leads to a radiative recombination, but it can also be quenched. It can transfer its energy, and then it's lost, so to say. It cannot recombine radiatively anymore. And this quenching here of these excitons, that's what we find in OLED literature, leads to generation of trap sites, which in turn then increase again Shockley-Rittal recombination. So you see here that's already quite a complex system for which simulation and modeling is then a good tool to look into it. So you find in OLED literature different ways of how to model, and that's what this field cares mostly about. It, like in solar cells, the maximum power point tracking with time. You have here the luminance decay at a constant current, and you can see here several examples of how different models, either analytical or also a full drift diffusion model, were applied to understand this degradation in OLEDs. And the core of these models is the evolution of the trap or quencher concentration with time, and also laterally or through the device, with which results of different processes. You can see here it can either be, you can either have just a simple trap site generation from the whole profile or electron, but what's mostly looked into in OLEDs is this exciton polaron quenching, where the exciton is quenched due to the hole density. So I show you an example in Setfos, where we have conveniently already a model in a tutorial file. So if I look into the OLED files, I open here the degradation example. So for those of you who are not familiar with Setfos, I just quickly introduce the user interface. So you have here, next to the files which I open now, you have here the definition of the stack. So here you could add another layer, for example, which we don't need at the moment. And then for each of these layers, you define your parameters in first base. That's the optical parameters here for the emission layer with refractive index, real and imaginary for absorption. And then, of course, also for drift diffusion, you define your parameters for the charges and, for example, also the charge mobility, which you can see here is in OLEDs often field dependent. You define your excitons, or your exciton, your one exciton in this case of this example. And importantly now, you can define your trap here. So we have one trap defined, and you can here put in the trap energy. Conveniently in the energy level section here, you can see also where your trap is situated according to the parameters you set. You have here capture rates. So at the moment there is a model based on the parameters we put into the model defined, but what you often find is also a constant capture rate. And lastly, here is the degradation model, where you can choose which events lead to trap site. And what you see here is what's defined is exciton polaron quenching for holes. So if we look into this equation here, that's just the light blue part, which is now generating trap sites quencher concentration with time. So we can run this model or this file here and play around with it. So the first thing we could do while this is running, I turn off the degradation model to see how this looks like in comparison. So the files are generated here on the side and we can compare it later. And what I also do now as a comparison, I turn off the Shockley-Rittal recombination. I will explain in a second what this means. What I'm doing is I'm setting here the electron capture rate to 0. So what I did now, just to show you this, is in the Shockley-Rittal model, I turned off here the electron capture rate, but what's still going on is that holes are still trapped. So you still get the hole trap density, and this hole trap density also influences the whole system. So we can have a look at how these different simulations now look like. So in first case, if we look directly at luminance transient with the degradation model disabled, you see here with time there is no change in luminance. If we have this trap site which evolves, there is a big change in luminance with time. And if we turn off the Shockley-Rittal recombination, you still see a decline of luminance. Now, to understand this, we could look into the model, what's going on. We see that less traps are, or a different amount of traps are generated, and you could, if you would want to look deeper into the different profiles of charge densities to understand what's going on here. Last interesting change is, of course, you can have a look at different models of what effects or factors are leading to trap site. So instead of hole polaron, I choose now electron in combination with excitons to lead to trap states, and to kind of have a look at how then the luminance curves looks compared to the whole exciton or polaron exciton quenching. And you see that now with choosing electrons as a quencher, nearly nothing happens. So this looks surprising. So we could look into the model, what's going on here, and see that, okay, in the model we had here, there is quite a low electron density compared to the hole density. So in turn, also you don't generate much traps because of that. And you could look further into that. But I will go on now with the thermal model, which can also be used for solar cells and OLEDs. Again, I start with the OLED side to show the different aspects of the thermal module or the different thermal models. So the first important one specifically for OLEDs is Joule heating, which is essentially resistive heating. So you drive a current through a resistor with an applied voltage, which leads to heating. And this Joule heating, if you go in OLEDs to larger current densities, you can see here, leads then to quite strange effects, because the heating itself then influences the electronic parameters, and you can get quite some peculiar shapes here, which you can model. But even before this effect, if I go to lower voltages, where the current starts to rise slightly, you see these changes already in impedance spectroscopy features, for example, as another low frequency features you can see here. To model this, you need this self-heating, you need Joule heating. That's the first aspect of the thermal model. Second one is heat lost or heat generated because of recombination losses. So everywhere where you see here this flame, that's where heat is generated, either here in a dark chocolate Hall recombination, the energy gets transferred to heat. Also, if excitons are quenched, the energy can also get transferred to heat. So you need to consider this in a full model. And the last element I'm talking about now, back again to solar cells, is the optical heating. So the thermalization, if you absorb a photon with a higher energy than the band gap, then the energy of the electron, which gets dissipated while going down towards the band gap, that's lost in heat again. So to look into this, I set up a quick model. It's not the full Shockley-Queisser model in Setfos here, because we still have optical losses, as I was modeling the optic part still with a realistic refractive index. But you get the same trend here with the model when shifting the band gap of the perovskite here, as you can see, for the power conversion efficiency. You can look at the non-absorbed photons which are not absorbed. So the dark green here is transmitted photons through the device which are not absorbed. So you see here there's still some reflection. That's not part of the Shockley-Queisser model, for example. But what we can do now is look at this thermalization part in more detail. So here you can see the same trend where you have higher thermalization the lower the band gap is, because more bigger part of photons that are absorbed are lost in heat, so to say. So we can go into back into the model again and look at this file in more detail. So what I set up here is to go towards the Shockley-Queisser limit. It's just one absorber, and you see here that the injection is perfect level. There are no injection barriers. As I said, I still have a model here, an optical model. So what we're looking at now in the results is directly at the generated power, where we now can split up the heating we saw before and look into the different factors. Now in this simple model, the biggest part, or in general, the biggest part is the thermalization. But even in the simple model with no recombination heating, for example, we see there is this Joule heating, which you cannot avoid, as you need to extract the charges. So there will be some field, some voltage loss and current. So you will have Joule heating, and that's part also of the Shockley-Queisser model. Now it looks like that this Joule heating is like it's not dominating. The whole situation is dominated by the optical heating, by the thermalization. But if we go towards higher band gap, you can see here that these two factors getting closer. So if we have a look at again full model at a higher band gap of 1.6 eV. So you see here again with the transport layer simulated and injection barriers, along with some Shockley-Hall recombination. If we look at the results of this simulation, you can see here that the power that is lost in heat, the heating power, has quite a peculiar shape when looking at or when just looking through the swept voltage from JSC short circuit towards VOC, and that's because the Joule heating is getting comparable to the thermalization. And just to understand this curve better, if we look at the device current here, the simulated one, if we go from maximum power point here towards short circuit, for example, you extract less and less energy. So if we look at the electrical power with the maximum power point here, if you are at short circuit or at VOC, you don't extract any energy anymore, which means in turn that this energy must be again dissipated in heat. And What's important now is to understand how this heating power is translating to actual cell temperature. So in the model I chose here, you can see that this power translates only to a minor temperature increase here from 300 Kelvin was chosen as rough room temperature environment. But that's because, and now we are looking into some of the parameters of the thermal model, that's because if we go to the boundary condition, which is set up as a convective boundary, so you have airflow, for example, this parameter here, the transfer coefficient of 100 watts per square meter and per Kelvin, represents a very strong airflow. So if we want to have a look into how the temperature changes if we go set a parameter which represents no airflow at all on both sides, then we can run this example, and I have to put here the voltage sweep to only 1.1 volt, otherwise the simulation takes some minutes, which we can't do now in the live view. So with nearly no airflow, you can see here that the temperature effect is now quite drastically compared to the case if we have very strong airflow. So with this model, you can look into this. You could now look into what's happening if we go towards 85 degrees. Of course, you see here there's both air on both sides. If you measure a device, typically you would have on one side a direct contact, so this changes the situation. But this situation would be representative for if you would put a device on contacts and it's somehow surrounded by air, not laying directly on the heating plate, for example, or some other material. So there is more to this story of a thermal model, but I will not go through all of it. I just want to mention here that the model also considers Thomson, Peltier, and Seebeck effects, which are for certain devices very relevant, but as it turns out, these are also relevant to model. It's not dominating, but model part of the heat that is generated in solar cells and OLEDs as well. So you can find more information on these models if you're interested on the webpage here, and you can always request a free evaluation license. So with that, I finish my part and go back to the questions. Let's see if there are already questions here. Fanny, if you are here.
Yes, I am here.
Okay, perfect. There are some questions in the stack, and I will start with you.
Okay.
So first of all, I was wondering myself, because I also did work already with degradation experiments on perovskite cells, and they can be quite time-consuming, especially if you do several tens or hundreds of hours. Did you maybe learn anything how to deal with it, how to organize these experiments, or did you also try to go to higher temperatures to have a faster degradation?
So I understand what temperatures are relevant for this experiment, more or less. That's your question.
Yeah, as well.
Yeah. I think that the temperatures we have done experiments at 65 as well. So the study that I linked where we looked a little bit at this shunting, we also see it at 65. But in our case, we think that 85 was the kind of maximum temperature that we could use while still adhering to the ISO's protocols. So we're really trying to accelerate the degradation in this case. I mean, the study itself, each study was less than 24 hours. So it's quite a fast evaluation and we could get a lot of information. I don't know if we would go higher, we go into a risky zone where it would be very difficult to compare our results. But yeah, I mean, of course, you could go higher, but you will have different domains, I would say, of degradation if you go too high. And in this case, we didn't see any crystallization of new materials or similar. But I can imagine if you go too high, you'll start to see maybe more lead iodide formation. In our case, we didn't see any lead iodide changes.
Yeah, I see. So did you get any notion that like you introduce a new or different degradation pathways when going to higher temperatures? Or was it rather, I was always wondering when switching from 60 or 65 to 85, whether I would introduce completely new or some degradation pathways start to dominate or something like that. How was your perception here?
I think that the general trend that we see with this shunting and also the recombination changes, I think that's consistent for all higher temperature degradation. However, the sharp voltage drop when we just introduce 85 degrees, I think that can be very much because of the more extreme conditions. To go immediately from room temperature to 85, that's kind of a big jump. Of course, that could happen, but maybe on a lower time scale. So that would be the most extreme part. I think that when you perform changes to your device, so you're suddenly adding stressors, you have to be very careful that it's realistic. So if I would criticize a bit, I would think, yeah, well, we increase it gradually, but we have to think about the scenario. Yeah, maybe leaving the elimination on for a bit. I would be curious to see what happens.
Yeah.
Mm.
A question which popped up is so you also worked on strain publication specifically with respect to strain. Since I also myself didn't come in contact yet with this keyword in degradation, can you stress or highlight how, like, what's the factor strain in degradation?
In this case, what we've seen also in previous studies is that we see when you have expansive strain, that's really detrimental to your stability because the interatomic distances in your lattice are really becoming larger. So that makes it easier for things to move around. So if we already have a rather soft lattice where we have ion migration or a formation of defects, that can be enhanced when we get an expansion of the lattice. And we've seen that if you're able to produce a compression in the perovskite lattice, you will see also that can enhance the stability. However, you also have strain that can occur from an interface and out into the perovskite, and in that case, it's not so clear. So we've been looking more at isotropic strain, so it's a little bit similar in all directions, and we're still maintaining the cubic lattice of the perovskite. But you will also have anisotropic strain where you can have deformation of the symmetry in the crystal. So in general, strain is always going to be there because there is going to be a response to outside stressors, but we have to make sure that the thermal expansion that we're seeing, which is the type of strain, in this case, that it's able to exist without being detrimental to the performance of the cell.
So in a sense, this strain is indeed another factor to consider when one wants to analyze degradation.
Yes,
in the perovskite solar cell.
Yeah, especially at higher temperatures. And you also have to consider that we're annealing the solar cell at usually like 100 or even 150. And when we cool down the solar cell, there can also be an introduction of strain. In our case, we're using the mesoporous TiO2. So that's actually an advantage for using the TiO2 layer because since it's mesoporous, it can compensate for strain during cool down better. And if you look at the other study that I linked in ACS Energy Letters, you can see that we did a complementary study where we actually showed that due to the mesoporous layers, we don't have residual strain in the perovskite. But of course, as we're heating the cell, the interface between the perovskite and the HTM is going to strain because there we have like more between spiro and perovskite, we have a more direct adherence. And when we add a Maxim layer, we really improve that scenario. So we make the contact between the two layers a little bit more forgiving.
Yeah. Oh, on that note, if we talk about layers, is there what's the relationship between the characterization of thin films only and full device? Is there a difference?
Yes, that's such a big difference. And I think that we can get very confused when we look at other studies where you do just thin film or even single crystal on glass or single crystal on silicon or any type of single crystal growth on top of another material, because the strain conditions are so different. So I think that we should move more towards characterization in full devices. Even if you're doing stability testing, just try to at least have half stack to just have if you can't have layers on top, we'll try to have the stack completed as much as possible. I mean, I guess this is true also for time result for luminescence and everything, but it can become more complicated to interpret the results. And I think that's why it's so important to be able to do simulations as well. So you can explain what you see in terms of more layers, and it really helped us to be able to simulate a bit what we saw to see if we can get the same thing.
Yeah, on this note, I mean, I also worked during my PhD with drift diffusion software, with Setfos actually as well. And some processes are just too complex to understand, especially ionic ones. What do you think if you would have a model that includes different ionic chemistry? Would this help you much in understanding what's going on and link then the degradation you see to the further material characterization you did? Did you?
I think it's great to have more options. I think you should always link the simulation in actual experimental results, because I think the reality is when we really had a lot of experimental data, so we have so many cells where we've done impedance before and after, and we could really be very confident in the trends that we saw. And we also had a theory of what could be the reason behind it. So when we went into the simulations knowing that, it was really straightforward. I think it's really beneficial to have, as you're talking about, thermal models, to be able to see how the temperature changes. And I think that it's going to be very important to be able to select what type of ionic species, because maybe you have many parallel effects. I thought that was great with Setfos, that I could just, in our case, I believe we were working mostly with vacancies, because that's more straightforward. But I think, hopefully in the future we will have more detailed data. I hope more people will do studies with more statistics on impedance data, and then we could have more knowledge about which ions are moving, because in the end, in our case, we couldn't confirm. We were just, I think we could probably with this data do a lot more simulations, and we would obtain more understanding already from the data that we have.
Yeah, I think that's a good note to close the questions on your part. I also believe that it will be necessary to solve long-term stability, that we increase the knowledge of what's going on exactly with this ion chemistry, and that's still ongoing work for coming years. We will see. I will just answer a few questions we had on the model side. I got asked if it's it's possible to simulate OPV stack. I don't show this now, but as I showed before, there are quite a few, about 5 to 10 examples of OPV in the tutorial, in the example files. Some of the questions got answered already by our product manager actually of Setfos, himself. Okay, yeah. I think with that, I close today's webinar. Fanny, thank you very much for your contribution. Truly interesting. Thank you everyone for joining, and have a good day.
Thank you so much, Matthias.
Bye
Thank you
bye.
everyone for joining.